I'm sure all of you can write it down. Can somebody try for that quick?
Sir, roll number, sir. Codomain ranges from 1 to 64.
Oh, roll number and okay. What about codomain ranges from 1 to 64? You are giving roll number. Okay, what is the domain?
Students.
Set of students in our class and the roll number. Can somebody try another one? Another some other thing. This is okay. Whatever you said is fine. There is one as well as onto. Each of you having one native place. So it may be a village or a town, whatever it is. So student set of students, I am taking a function. I am taking a function from set of students in our class. Oh, that also may be different. It may not be bijective. Two students may be from same native. Okay. Slightly modify that. I am considering domain is set of students. Codomain is their home. That exact building or whatever it is. So if there are no twins in our class, if there are no brothers and if there are no two students from the same family, then we say that by a function is a bijective function. Look at your timetable, time versus the class. Again a bijective function, meaning you give me the time, there will be exactly only one class ongoing there. You give me that class, then you can find out the time also in a particular day. Okay, not a week. Take a day and you have this timetable and your classroom association in colleges. Each class will be given a room, so you can sit there. That is one function as well as onto function. Suppose if nobody sits there again, no other class is allowed to sit. Consider the faculty rooms in our college. Each faculty is given a room. That room is allotted to the faculty. No other faculty is staying there. So many things you can do, and these things we have elaborately discussed. And then we were talking about fundamentals of logic. Not only this, before that, graphical understanding. What do you say? Horizontal line test. Let me say that name here. Horizontal line test. Using horizontal lines, how to check whether a function is on or onto. In fundamentals of logic, we considered 5 connectives. Connectives are, first of all, we consider this not, then or and implication and both implies. This symbol we shall use for both implies. Somebody write this symbol also. We shall use this since we have used single line for the implication. We shall use both side arrow for double implication. We have seen some of these already, and some of these we have not seen. And what it be so what we have seen, and also we have seen truth tables. What we mean by truth tables, and what is a truth table for PRQ, P and Q, all those things. So we have not discussed that, I think. Truth tables you can write down. So maybe quickly we shall do one more thing. So let us use P and Q are two propositions. Proposition we have defined already what they are. It is a declarative sentence. We can assign a meaning, or we can assign a truth value, T or F. That kind of sentences. It is an English sentence with that property. Sometimes you call these as statements. All those things we discussed. Now I'm giving P and Q. P R Q I want to write. Just listing out the truth tables. Okay. Not only this, let me write down another truth table also, another one truth table. I think we have not written the truth table already. There P R Q we have written, P and Q I will write now. P implies Q. I am not spending too much time in this. P R Q I am defining now. P R Q refers the truth value. If both are true, this is one of them must be true. If both are true, I also agree that T. This is inclusive R. Let me use inclusive R. That means either one of them true or both of them is true. Then I will have the truth value as true. If both are false, I will be having false. Here I need both of them must be true. Otherwise it is false. Here I need implication. If P is false, I don't need to check Q. P implies any Q. So this is true. So you don't want to forget that, then you may use the explanation we have given. Your teacher is not teaching good, then in that case, education system will agree that whether you get pass or fail, that will be a progress, because the input itself is incorrect. Okay. Suppose if the teacher is good, then you need to be good definitely. Otherwise, the system will not agree. We have two observations. If Q is true, these two observations, okay. If Q is true, always the implication is true. If P is false, always the implication is false. So two observations we made on that day. So when you want to check implication, you need not check all these things. You can check only if key is true, done, completed. Then the implication is true. Or else you have to check if P is false. Only this thing is enough. Okay. So we call this as implication. One side implication. And we call this as and then we call this as R, inclusive R, of course. All these things we have done already. Probably I have not written this table, which you know already. Now, this implication can be written in various ways. That's what I have listed here. P implies Q. If P, then Q. These are various forms of writing the same P implies Q. In constructing proofs in mathematics, you want to prove something. Step by step, we will do your computation or your inference, that I'll say, your deductions. You deduce from the previous step. You are going to deduce the next step. From the current step, you will deduce the next step. That kind of deductions you will be writing using English and also our symbols. Whenever on the screen you have 2, 4, 5, 7, 11 implications are there. All of them are same. in disguise, that's all. If I say if P then Q, that means P implies Q. If I say Q follows from P, that means P implies Q. All these things are same. Just I am listing down. These are possibilities for writing the same sentence in disguise. Let us look at the fifth connective, if and only if. The symbol we are going to use this double implication with single line. It is having two parts. This P implies Q implication and this implication. Actually, if I want to write down this, I will be writing P implies Q and Q implies Q implies. I can write this also. P both implies if this happens. Actually, now only I am defining. So I will not use this implication again in this place. If I write like this, we are defining this double implication. In that I am using this double implication. So I am defining using the truth table. First, let me write down this P implies Q. Can somebody tell me this P implies Q? Vertically, I want to write down. P and Q are taking these two possibilities. Can you tell me P implies Q? Quick.
True, false, true, true.
True,
False.
false. True, false.
True.
True, true. Okay.
False.
Q implies P.
False. True.
True, true, false, true.
Q implies P. You are going to check this, whether this is happening or not. Okay. This implies that. Okay. F implies T. It is very good. Teacher is bad. Student is done. Student is doing fine. This implies that. Okay. Or if you have difficulty, you write Q and P again, then you may do it. True, true. What happens to this finally? T implies F. That we don't agree. F implies F. That's fine. Is this what you said?
False. False. True. True.
This one?
True, false, false, true.
You are saying finally for this true, false, false, true. So these are the possibilities. Suppose if you are getting this truth table value that is defining this P both implies Q. P both implies Q is defined above. It has two subdivisions, one implication and another implication. You see here two implications are connected by a connective and. If some of you are not following this, you can ask me. I can explain separately also. And also, if you don't follow anything, you just stop me. We shall give some more analogies or examples so that you can understand properly. Don't hesitate. You can stop me at any time. Till this, we have seen 5 connectives and how do we use them in sentences, or what is the truth table, or how they are defined. They are defined by these truth tables, or they are explained by these truth tables. If you write P implies Q, or if you give me the truth table, I understand both of us are same. Both of them are same. Now, next thing I'm defining. Propositional functions. So far what we have done is, we have done functions first. Also, we have seen what is a proposition. Proposition is a declarative sentence to which we can assign T or F. the truth value. In this slide, I am explaining each proposition we can write as a function. Look at here, I am writing this negation symbol is a function from this domain T comma F to the codomain T comma F. Just before that, let us look at if P is true. This implies negation of P is false. P is false. This implies negation of P is true. Not only this, in this way also it holds. Because P and negation of P, if I give me any proposition, only one of them is true, the other one is false. That's what I have written here. It is taking values from these two possibilities, T or F, and it assigns value from these two possibilities, again T or F. Give me any proposition, the negation of that can be viewed as a function from this set to that set. You are giving me a proposition, I am looking that as a function. Why do I look in that way? Let me write down whatever I have written here. Let me write down in terms of a table. Suppose if I have P and negation P. You see, suppose if this is true, this is false. If this is false,
True.
this is true. That's what I have written there already in red color. Maybe the same color we should. Okay, let it be there. When you define a function, what usually you do, just let me recall, function is from real numbers to real numbers. You have to define what is that function definition. Some other thing we shall use. Function is from real numbers to real numbers. Then you are defining f of x equal to say sin x, something like that. This is just an example, okay? Here, instead of f, you are using this. Then you have to tell me, what do you mean by this f of, instead of small x, you can write this. Instead of small x, what is the truth value of this? Maybe let me write down. If P is true, what happens? Negation of this is truth value of P. Wait a second. Whatever we have written in red color and the green color, I am trying to write down with this notation. This function, instead of x takes values from the domain. So I have to take value from here. This is truth value of the proposition. This function takes that to truth value of that, negation of that. We shall not write this P here. We shall avoid that for instance. Simply I am writing this symbol. That's it. Tilde symbol I have written here. Even if you write a tilde P, that's okay. Now, what is the explanation for this? Here, observe, the function definition is completed. Observe, tilde of truth value of P. Suppose if P is true, negation P will be false. Suppose if this is true, then the negation will be, if this is false, the negation is true. Are you understanding this? Both elements T and F are having image in the codomain. You can define a proposition as a function. Are you understanding? Our connective or our proposition changes this truth value according to its nature to another truth value. Sometimes it may not be changed, but this symbol delta is negation that we are looking at a function. It changes the truth value, exactly the opposite. Are you following this? Or if you want to write down the same thing, instead of this tilde, you can write tilde p. But still, it holds the same. Let us keep in this way, because this is our propositional function. This notation we shall use instead of f. Are you following this? Can someone ask me some questions in this? Instead of small f, I am using this tilde symbol, new symbol I am using. That gives me a function. That is actually a proposition. Tilde p is a proposition. Shall I write one more thing? We shall go for the next one. Another example. I am writing this R symbol. R symbol needs two inputs, P and Q. Look at this is Cartesian product. Two inputs that needs. But the final output, P or Q, look at the table. Okay. It needs PQ, P or Q. If both are true. All these things we have done already. Let me quickly write down. This is okay, this is okay, this is okay, and this we don't agree. One of them must be true. This we have seen already. Now I am defining this PRQ. This is a connective. So this I am looking like a function. A function which needs two inputs. First input may be true or false. This is the first input. First input. Or simply let me write down P. Maybe true or false. This is Q. This is PRQ. That's what I have written here. PRQ is a function. Or if you don't want to PRQ, you can simply write just a symbol. This symbol gives us a function. The same thing I have written already also. So instead of this, we are writing what happens to this. If this stands for P and this stands for Q. Now, this function operating on these two truth values. P is true, Q is true. What about this function? This function takes these 2 points to a specific truth value which we called as true. Are you understanding this? This is, suppose if you want to explain, it will be like f is from R cross R to R. F of x comma y is say x plus y. Something like this. Give me 2 inputs, I will give you 1 output. Here also you are giving me 2 inputs. For that I am assigning 1 output. If P is true and Q is false, 2 inputs you have given. I am assigning 1 output. Are you following this? The red color truth table we have seen already. That is actually having two inputs, one output. So I'm writing that as a function. Whether you use this symbol only or you are using P or Q, both are okay. One more thing we shall. Are you following this? Earlier we were spending too much time on functions, and then we have seen propositions. Now I'm saying proposition also can be written as a function. What I would say, for example, suppose if you have implication, here you have written implication is this. So this thing we shall do one more way. The implication also can be written this implication. Is it visible?
Yes, sir.
Let me take a little larger also, no problem. Just I'm trying to write down with different notations, that's all. You can use any one of them. Both are okay. So here, look at the left side, I'm using this symbol. Now I'm defining that. Only 4 possibilities I have, so I'm listing them out. So this is defined by implication. If instead of the first entry, I'm taking P and then Q. Okay, P is T, Q is T. If both are true, this implication is also okay. If teacher is good, student fails. That's not correct. If the teacher is not teaching well, then I always agree that system is okay because student has no other choice. You see, I don't memorize these values, then I may forget. So I'm keeping one appropriate example always. Instead of this, I can write the same thing I am writing here also. Then what's the difference? The difference is that actually there is no difference. Only the notation difference I have used. If in some textbooks, if you have seen this, instead of this, I have used only the symbol here. Both are okay. Is it okay? Recall the truth table yourself. I'm not writing down. That's it. So again, this implication P implies Q is viewed as a function from two input set, a Cartesian product of these two things, to single output set. Our propositions and our connectives as well, and our functions are related. Now I ask you one thing. I'm having all the propositions in my hand, all possible propositions. And also I'm having all possible functions, two different classes I have. Which class is larger? Which is a special case of what? Whether proposition is a special case of functions or functions are special cases of propositions. Can somebody tell me that?
Propositions are special case of functions.
Propositions are special cases of functions. Then in that case, functions are larger class. Functions are larger in size. Okay. Maybe you can go through that also. This is another proposition. You can try for the truth table. All the connectives we have written, I think. The connectives, whether we have written all the connectives, just check. And symbol, R symbol, negation symbol, both implication symbol. This both implication is actually double separate implications. So that is having inside. Single implication also is inside there. You can check the truth value or truth table. Before that, observe this can be viewed as a function with 3 input values. 3 input values. P, Q, R are input values. Do you see that? Can somebody tell me what is the domain for this function? This is a proposition. You will write the truth table, whatever you have done already till in school level also. Now I ask you, suppose if I write this as a function, can you give me the domain of that? Quick. I need domain of this propositional function. Can somebody try that?
Cartesian product of P, Q, and R.
Domain. Cartesian product of, you want this?
Yes, sir. P will be P, Q, R will be either true or false. Sir.
True or false? Cartesian product, true
Yes,
or
sir.
false? Cartesian product, true or false? I need set. So whatever you have tell me, the second one, that is set. This is your thinking process. See, I have striked out the thinking process. That's a rough work. You are expecting, actually, you will not write Cartesian product here. These are not sets. You will be writing PQR. You need this triplet. You need this triplet value. It may be true, it may be false, any possibility. 8 possibilities are there. So this also I will strike out because this is your thinking process. This is the domain. Codomain is just 3 input values, meaning 3 variables. Okay, that's it. Codomain is just a set. Take a MIF only. Okay, then we'll proceed further. We have 3 special propositional functions. First one, logically equivalent propositional functions are simply logically equivalent propositions. Meaning, you give me an expression like this. Somebody is giving another expression. That expression is actually the proposition I am talking about. So, 2 propositions are given. What is the relationship between them? If they have the same truth table, I say they are logically equivalent. Two different propositions are given, not single. Here I am using this also as proposition. P separately, Q separately, R also are propositions. That's okay. Singular and plural we are using synonymously here. A proposition is an expression involving the truth values, involving statements or propositions again. Or instead of this, let me say this is an expression. Let us keep that way. We shall be having expressions involving many propositions connected. So somebody is giving expression 1, another student is giving expression 2. If both of them are reaching the same truth table, I call those expressions are equivalent. Or according to this, function definitions will be same. Logically equivalent propositional functions. You are giving me 2 propositional functions separately, but I see that they are having the same truth table. Or I see that they are having same function definition, exactly the same function definition. Then I call them logically equivalent. How do I verify? Either I should have the function definition for all the terms, or I should check using truth table. Can you give me some such thing? I need 2 expressions, truth table must be same. Can you try for that, or shall I give? Let us just look for this. P implies Q. As an example, let me give you, okay, definition. This example, let us try for that. P implies Q. You know the truth table, or you can view this as a function. I'm saying this is equivalent to not Q implies not P. This is an example. This is not the only example. You can write many examples. Before that, let us check whether this is happening or not. Some equivalence is written already. That's okay. First, let me check. In that place, we shall keep these things in the next page. Later. Now we want to check this. Is this happening? How do I check? I have to check by truth tables. P, Q. I want to check P implies Q. Not only this, I need a not P and a not Q also. Then I want to check this, and also not Q implies not P. These many things I want to check. I want to check whether this left side expression and the right side expression, the connected propositions, whether they have same truth table or not. As usual, the possibilities I'm writing down. So not P refers negation of P. Here it comes there, okay, negation of P. So it is FFTT. Negation of Q is FT, FT. P implies Q. That I have already discussed. P implies Q. If Q is true, that will be implied always. If this is okay, this is not agreeable. Not Q implies not P. Whether this gives that or not, that thing we have to check. Only implication. You look at I am not worrying about what is P, is it practically possible, what is Q, whether my conclusion is valid with practical sense. All those things I am not worrying now. I am checking whether implication is correct or not. Not Q implies not P, not Q is false, so that becomes true. True implies false is false. False implies true. That's very great. True implies true.
True.
So what do I see is this, whatever here I have, I am having there also. I conclude that these two expressions are logically equivalent. You see, in mathematics, what we do is, if I want to prove this, I shall start with the left side. Step by step, I will be doing deductions. I will justify due to this property I am writing this. Due to the some property I am writing this step. Step by step, I will be keep on writing. Finally, I will arrive at the right hand side. Left hand side, I will start. Then I will arrive at the right hand side. That's what I call proof. Or you want to start from right side? Okay, start from the right side. Step by step, you do things. Finally, reach the left side. This is, I call as direct proof. Direct proof. But that I am not doing here. Here I am verifying with truth tables. That's okay. Whatever I explained, like proof construction, we will indicate soon. This is one type of expressions which are equivalent to each other. They have the same truth value. Just let me take this example only. Okay. This one, we have seen one definition and example. The same example I want to illustrate. I know that this is correct. I know that this is correct. Can I relate this with one function? That's my question. Are you understanding my question? First of all, I don't need anything else. I have already seen this application already. So what I do is that, just let me write down. F is 1 function from x to y is 1 or I have written that usually 1 if something happens. What is that something? Now give me two elements from the domain with this property. Then f of what we concluded? These two are different. That's it. Let me call this as statement P. This as statement Q. Here I have written implies, okay? Now the same statement I want to write down. That I am writing like for all x1, x2 belonging to x with, you see this P implies Q, I want to write as not Q implies not P. Or you want this implication symbol, we shall write that, no problem. This implies that not Q is negation of this statement is f of x1 equal to f of x2. This implies negation of this statement is x1 equal to x2. Following this, based on the truth table discussion, we have seen that this is actually not Q, implies not P. These are equivalent definition. F is on 1 if this is happening. Are you following this? We have used this already. Are you following this? Someone speak.
Yes, sir.
Oh, it's already 9:50. We shall just indicate the next one. We shall stop with that. This is one example. We need one example for this. This tautology we want to define. It means implication is true always. P implies Q is always true. That we call as, maybe these things we shall discuss in the next class. We shall stop at this point. It's time. You have any difficulty, you can just ask me at any time. Okay. You want to ask me anything now? Then we shall stop at this point.
Thank you, sir.
Thank you all.
Thanks, sir.
Thank you, sir.
Thank you.